Matt Parker on the awesome YouTube channel Startup Maths recently made a video about dithering, where dithering is basically you have an image and you want to recreate that image using only two colors, pure white and pure black. So if I snap my fingers now, I've dithered, which what's happened, this is applying the most basic dithering algorithm possible in the most naive way, where I've set some brightness threshold and every pixel in this image above that threshold has been set all the way up to white, and every pixel below that brightness threshold has gone all the way down to black. For all the dithered shots in this video, I've also lowered the resolution down to 480p to make the effect more obvious. So with this naive algorithm, you can see some details. It's kind of working, but the result is not great. There's just all of these big chunks of solid continuous black and solid continuous white all over the image where all of this information has been lost. Like up here we've got this just empty void, or my face looks even paler than it does in real life. And so Matt's video that inspired this, it was all about just ways to do better than this naive approach. And I got, nerd sniped by his video. I wanted to implement my own dithering, and I came across this class of algorithm called error diffusion algorithms, which he didn't mention, but I think are way better. To understand why error diffusion algorithms are really good, it's good to start with why this shot is so bad. This shot is so bad because lots of regions have just been flattened out to completely white or completely black, throwing away everything. And that happens because the value of a pixel in an image is very closely correlated with the value of the other pixels in its vicinity. To illustrate this, I've made an animation. Here we've got a photo of my niece and my son. My niece is standing out in the light, so if we zoom in on her, all of the pixels here are closer to white than they are to black. Importantly, they're not exactly white, and so we don't want this patch of the image in aggregate to be at maximum brightness. But because every individual pixel is closer to white than black, when we apply this threshold, they all get clamped to pure white. If you think about the difference between the brightness this pixel was after we dithered it and before we dithered it, for every pixel here, that difference is pointing in the same direction. Every single pixel got brighter than it was supposed to be. In the same way, if we zoom in on my son, who's in the shadow, over here, we don't want this to be pure black, but every individual pixel is closer to black than to white. So if we apply the thresholding, that's what we get. Every single pixel gets clamped down to black. The error for each of these pixels is negative every time, and so the patch taken as a whole ends up very different to the original image. And that's why if we apply this across every single pixel in the scene, it looks less like two cute kids and more like a scene from a horror movie. So how can we do better than this? In Matt's video, one option he showed us was adding random noise to the image, as in, before we apply this threshold to every pixel, let's randomly increase or decrease the brightness of each one, and then apply the threshold, so that some might just randomly flip from black to white or white to black. And I'll do a split screen here, where sort of on this side of the image, we've got the original naive dithering algorithm, and then on this side, we've done the same thing, but before we thresholded the pixels, we added random noise. And as you can see, surprisingly, adding the random noise actually makes it better. This doesn't usually happen. Like, noise and signal should be kind of separate, and it shouldn't be that by adding random distortion we've improved the clarity. In this case, random noise is statistically more likely than not to cancel out the other distortion we introduced with the clamping. I guess one way of thinking about how this random noise can actually help is to consider that any image we're actually going to be interested in is going to have some structure to it, where there's going to be regions where all the pixels within that region have a similar color. Like, all the pixels on my shirt are a similar color, all the pixels on my face are a similar color, all the pixels on this chair are a similar color. And like we saw before, when that happens, if that dominant color is below the threshold, all the pixels become black. And if that dominant color is above the threshold, all the pixels become white. So when we do that, when we make every pixel in the region white, we're minimizing the error at a per pixel level. Every individual pixel is getting as close as it can to its original value, if the only choices are black and white. But on a sort of zoomed out region level, because every pixel in that region gets made white, every pixel errs on the side of being brighter than it's supposed to be, the whole region has a lot of error. The whole region is very different brightness to what it was supposed to be. So if random noise happened to make some of those pixels flip their value, so within this mostly white region we get a few black pixels, that can lower the error in that region. Even though the individual pixels that flipped, their individual error got way bigger, the aggregate error can get smaller. And it's got this nice property where when we go to threshold or region, if it was just above the brightness cutoff and then we set it all the way up to white, that's kind of the worst case. That's the case where we create the most aggregate error. And at the same time, the closer it is to the threshold, the more likely any individual pixel will get its value flipped by random noise. So the random noise just happens to play really nicely with the thresholding in this situation because of these kind of natural images have this structure of like continuous regions of a similar color. But we can do a lot better than this using error diffusion algorithms. These algorithms basically say, well, we could use random noise to, in expectation, make the image better by relying on these sort of two separate cases of distortion cancelling each other out. Or we could fix it intentionally by deliberately keeping track of the error we introduce each time we increase the pixel's brightness or decrease it. So that's what an error diffusion algorithm does. As we scan through the image, we remember if we made this pixel brighter, then on the next pixel, we're more inclined to make this one darker, aiming to, across the whole image, try to keep that aggregate error as close to 0 as we can. So in a manic state of Claude Code psychosis in one of 7 terminal tabs, I've made another animation to demonstrate these error diffusion algorithms. The algorithm this is going to show is Atkinson dithering, named after its inventor, the legendary Bill Atkinson of early Apple fame. I think they used this algorithm to display images in the original Mac Paint software. So what this animation is meant to show, these are meant to be pixels, and this is like a patch of our image that is some kind of middling gray brightness, where if we thresholded this whole section of the image with a 50% brightness filter, every single one of these pixels will get black, and that would be a terrible result. And so I'm going to show how error diffusion algorithms like Atkinson dithering deal with a case like this. So we'll start with this pixel in the top left. It's got 43% brightness, so because it is less than 50%, we are going to clamp it down to black. But when we do that, that kind of brightness that we're throwing away by taking this all the way down to black, we're going to donate some of that brightness to these neighboring pixels. So if I set this down, by making this black, we made the rest of these a lot lighter. We do it again for this pixel, where we treat this one as if it's done. We don't sort of take any from this pixel and try to give it back. We want this to run in linear time. But these 6 pixels here, when we make this one dark again, because it's below 50% still, we're going to donate more of that brightness to the pixels around it. So we do this again. And now you notice we get to this pixel number 3, because of the brightness that was sort of donated to it by pixels 1 and 2, this is now above 50% brightness. It would have been black if we'd independently thresholded every pixel, but because we've sort of tried to spread the error around, now this one is going to become white. And when we make it white, to correct for that, we're going to make the pixels around it become darker. And then so you repeat this process, and if you repeat this process over and over again, the result is we tend to spread out the black and white pixels across this image. What we want to see is the sort of average brightness in this region that is reasonably close to a middling gray. And that's what we're getting here. We're getting a really nice mix of black and white pixels arranged in a way that does give consideration to the pixel's original value and also doesn't create any artifacts of making every second row black or every second row white or anything like that. It's like a naturally distributed pattern of the right average brightness, or close to the right average brightness. All right, so now it's the moment we've all been waiting for. What do these error diffusion algorithms actually look like when applied to this shot? So we'll start off by applying the naive thresholding again, so we have a baseline to compare against. And in 3, 2, 1, whoa, would you look at this? This is a error diffusion algorithm applied to this shot, and look how much detail there is. You can see so much. You can see like the mesh of my chair. You can see my hand shadow behind the mesh. You can see the difference where the mesh is versus the backrest. You can see the feet of the lamp. You can make out the Hogwarts crest on the poster. You can make out how the skin folds in my hand. You can see individual fingernails. You can even see individual strands of hair. You definitely didn't get that in Matt's video. But something I still don't love about the shot is how it kind of looks like a snowstorm. All of these pixels are switching off and on really quickly, which is hard to look at. And it's also cheating, because if you switch a light off and on very fast, that's kind of the same as dimming it. And we're supposed to be just using full or minimum brightness. So to fix this, we'll do something called hysteresis, where on every subsequent frame, we'll be a little bit reluctant to swap the value of a pixel from what it was the previous frame. So we'll only change from black to white or white to black if not changing would cause a really big increase in the error. So I've applied that now, and it looks a lot nicer. Everything is calmed down. It's still a video feed. You can still see me moving around, but you don't get all of this just like chaos in the background of everything blinking on and off. I think it looks great. So thank you so much for watching this video. That was Error Diffusion Algorithms. While I was researching, I made a little web tool where you can connect your webcam and see yourself dithered and play with the settings. So that's in the description if you want to see that. Thanks to Matt for making the great video that inspired this one. This channel is getting super close to our goal of 4 subscribers. So if you like that stuff, please consider subscribing. I'll see you in the next one.